Some last problems to work on gas laws is collecting gas over water. This has a little bit to do with stoichiometry as well as Dalton's partial pressure. Okay, so stoichiometry comes from the fact that you're working with equations and you have to balance the equations and so on. And Dalton's total pressure or partial pressure comes from the fact that when you collect the gas over water, the P total is equal to the pressure of gas plus the pressure of water. Okay, so these are the partial pressures exerted by each of the gases. So why would you have pressure of water vapor? And that is because water is always vaporizing, unless of course it's 0 or below, then the vapor pressure is really low. But if you're working at room temperature at 25 degrees Celsius or above, then the vapor pressure of water is going to count. So if you collect gases over water, which is very common, then you have to account for the vapor pressure exerted by water. Now in this case, you will always have the data given to you regarding what the pressure of water is, so you don't have to worry about that. Okay, so if I give you any problem on that, I will give you the pressure of water, okay, at that particular temperature. So then you will find the pressure of gas by subtracting the pressure of water from the total. Okay, that will give you the pressure of the gas. Okay, so that's how the partial pressure actually comes into effect over here. So these are kind of like totality problems in some ways because you have everything going on. So let's work on the first problem. Calculate the mass of oxygen produced by decomposition of KClO3, which is potassium chlorate, when 821 milliliter of oxygen is collected over water at 30 degrees centigrade and 1.1015 atmosphere. Okay, and you need to have the equation, because if it's a stoichiometry, then you need the equation. So equation is potassium chlorate decomposes, which means we are getting two products. So it gives us oxygen and then it gives us potassium chloride. Let's balance the equation first. So we have 3 oxygen here. So put 3 here, 2 here, and then 2 here, and we are all balanced out now. And so then what are we doing? Calculate the mass of oxygen by decomposition of KClO3. Okay, and so how much of oxygen is collected? It is going to be 821 milliliters. So let's start working on this one. First of all, for the pressure. Okay, so P total, okay, is equal to the 1.105, okay, 1.015, excuse me, atmosphere. So you find then the partial pressure of water at 30 degrees centigrade, and you can use the tables for that, or I can, of course, I will give you that. This is usually given to us in torr, so we have to, of course, convert the torr into atmosphere. Okay, so the partial pressure or the pressure of water vapor at 30 degrees Celsius is 31.8 torr, so you convert that into atmosphere, 760 torr here, which is equal to 0.0418. It's a very, very small amount, but it is significant. Okay, so don't skimp on that. All right, make sure you do it, because when I grade your papers, I will be looking at that. All right, so then the pressure of gas of oxygen, okay, is going to be P total, which is 1.015 atmosphere, minus the pressure of water, which is 0.0418 atmosphere, and that is 0.973 atmosphere. Okay, so that is our pressure. So then the question is asking for how many grams, okay, of oxygen are collected. So sadly, this is not really quite a stoichiometric problem. P is equal to nRT, because all we need to do is find the number of moles and convert that into grams. It would have been a stoichiometric problem if we were asked of how many potassium chlorate, how many grams of potassium chlorate we needed. Okay, but we're not being asked that. We're just told that we have the volume of a gas and we need to find moles. Okay, so N is equal to PV over RT, and pressure is we just calculated 0.973 atmosphere. The volume is 0.821 liters, and then R is 0.0821 liters atmosphere divided by mole Kelvin times temperature, which is 30 degrees Celsius, and so you have to add 273 to that, and that gives us 303 Kelvin. Okay, so the number of moles that come out to be is 0.0321 moles, and now all we have to do is convert the moles into grams of oxygen, which is 32 grams from the periodic table, and this is 1.03 grams of oxygen. Okay, so the main thing here that was different from the normal problems is you had to find out the pressure, okay, of the gas, right? And it's not just the pressure of the gas, because you also have the pressure of water in there. Okay, so that was one example, okay, of a problem. The next problem that we're going to work on is a little bit of a stoichiometric problem. So here, hydrogen produced in the following reaction, which is over here, and that is aluminum plus HCl to give aluminum chloride and hydrogen. So aluminum is solid, hydrochloric acid is aqueous, and then this is aqueous, and this is gas. Okay, so hydrogen produced in the following reaction is collected over water at 23 degrees Celsius when the barometric pressure is 742 torr. What volume of the wet gas will be collected in the reaction of 1.50 grams of aluminum with excess of HCl? So luckily it's not a limiting reagent problem. We have excess of HCl. So aluminum is our limiting reagent. So 1.50 grams of aluminum. And the question is how many liters, okay, of the gas will be collected here. So we can do a few things here really quick, okay, so which means that we can go ahead and do our simple calculations first if we want to. And so this is 296 Kelvin, and then of course for the pressure, so now this is collected over 23 degrees Celsius of temperature, so we find the pressure pH2O at 23 degrees centigrade, and that is 21.1 torr. Okay, so to find the pressure of hydrogen, then it's going to be P total, okay, which is 742 torr. Okay, and so minus the pressure of H2O, so 742 minus 21.1 torr, and then we can go ahead and divide that by 760 to get our pressure in atmosphere, okay, right away. And so this will give us 0.9487 atmosphere. Okay, that's our data that we just collected. So now we can go ahead and start our problem. Our problem will be started from aluminum because that's what's given to us first, and this is stoichiometric. So let's balance the equation before we do anything at all. And here is aluminum, 2 hydrogens here. So to balance this out, we have 2, and then 6, and then 3, and 2. Okay. And so then start with aluminum, 1.50 grams of aluminum, convert that into moles. And in 1 mole of aluminum, we have 26.98 grams of aluminum, and 2 moles of aluminum gives us 3 moles of hydrogen gas. That's what we need from here. And so the moles are 0.0834 moles. Now again, PV is equal to nRT. We have to calculate the volume. So V is equal to nRT over B. Okay, and so then our moles is 0.0834 moles, 0.0821 liters atmosphere, mole Kelvin. You must be tired of this now, or you have memorized it by now. And then our temperature is 296 Kelvin, and our pressure, which we calculated by subtracting the pressure of water, is 0.9487. Okay, atmosphere. Mole, Kelvin, Kelvin gone, and we're left with liters. Okay, over here, and we come out with 2.14 liters, okay, of gas. So this is a nice problem where you're collecting gas over water and you're doing stoichiometry as well. I know, joy.